Hello everyone. So today we're going to go over section 3.13, exponential growth and decay. As it says here, in many natural phenomena, quantities grow or decay at a rate proportional to their size. So here's an example. On the top right, we have time equal to 0, 1, 2, 3, 4, and 5. And initially the population was 1. And as you can see, at every time interval, the population doubles. So 1, 2, 4, 8, 16, and 32. And you can see that it's doubling, which means that the growth is actually related to the size of the current population. So if the population was 1, it doubles to 2. 2 times 2 is 4. So if that's the case, it is then reasonable to expect that the rate of growth is proportional to the portion, and that is f prime of t. So if your growth rate instead of p, you call it a function f, then f prime of t, which is the growth rate, is equal to k times f of t for some constant k. Okay, so if that is the case, then we can rewrite it as dy dt is equal to ky, once again, where k is some constant. The equation is sometimes called the law of natural growth if k is greater than 0, or the law of natural decay if k is less than 0. It is called a differential equation because both y and dy dt are part of the equation. So for the specific case dy dt equals ky, the only solutions are exponential function in the form y of t is equal to y of 0 multiplied by e to the kt power. Okay, so let's look at what that means in practice. So we're given the world's population at 1950 and at 1960 years right here. And we're going to predict the world population in the second half of the 20th century. So we are going to assume that the growth rate is proportional to the population size, and that the growth rate is fairly constant. Okay. So first of all, this is a case where the growth rate dp dt is equal to some constant k times the population. If we were to isolate k, then 1 over p times dp dt is equal to k, which of course is the relative growth rate. Okay, so now what we can do is we can use the data that's given to us to solve for k. Okay, let's see how that works. We know that since we have a equation of the form dp dt equals to k times p, that the solution must be in the form p of t is equal to p0 times e to the kt power. Now, we are going to assume that 1950 is the initial time, so this is going to be t equals 0 for us. And 1960 is going to be 10 years after that, so t equals 10. Okay, so now that means we know that p of t in general is going to be equal to 2560 e to the kt power. Of course, then we can substitute in the 10, so p of 10 is equal to 2560 e to the 10k. So we know what that number is. We know that p10 is equal to 3040. So 3040 is equal to 2560 e to the 10k power. Okay, so of course we can divide both sides by 2560, so 3040 over 2560 is equal to e to the 10k power. Now we can simplify this fraction. It actually is just 19 over 16. And we're going to take the natural logarithm of both sides. So we will have on the left side simply ln and then 19 over 16. As I said, simplifying the fractions. In the right-hand side, recall that if we have ln, that's the natural logarithm of e to the, in this case, 10k, then we just have 10k. So now this is going to be equal to 10k. So k is equal to 1 over 10 ln 19 over 16. And this can be evaluated using a calculator. You get an approximate value of 0.017185. Again, we round it here. In other words, this would be 1.7% per year. Okay, so what this is saying is, over the span of those 10 years, the world population growth rate was 1.7% per year. Okay. Now, of course, that number fluctuates, and now it's quite a bit lower, actually. But regardless, let's look at the next part here. It says, estimate the world population in 1993 and in 2019. So 1993 is 43 years after 1950. Okay, so we're going to use P43, and then we're going to use the k value that we just found along with the expression that we had from before. So this will be P43 is equal to 2560 e multiplied by 43. That's the, sorry, actually let's write it out the other way. This would be 0.01785, which is the approximate value of k that we found, multiplied by 43, of course. That's our t value in this case. And if you use a calculator to evaluate that, you'll get 5,360 million. Now in 2019, that's 69 years after 1950, so that would be the same thing, except for you would change the t value here. Okay, and in this case, you'll get 8,379 million. Okay. So that's it for example 1. Let's look at example 2. Okay. So now that we've done exponential growth question, let's look at a decay question. Half-life of radium-226 is 1,590 years. A sample of radium-226 has a mass of 100 milligrams. Find the formula for the mass of sample that remains after, I should say, t years. Okay. Find the mass after 1,000 years, correct to the nearest milligram, and then we'll find them when would the mass be reduced to 30 milligrams. Okay. So again, we know that with radioactive decay, the formula that we're seeing earlier applies. So this would be m of t is equal to m0 e to the kt power. Because, of course, the rate of decay is dependent on the size of the sample remaining. Okay. So m of 1590 is going to be equal to 50, which is equal to 100, and then e to the k 1590. Okay, and we use the number 1590 here because this is, of course, the half-life. We know at that point the mass of the sample will be half of what it was initially, so this is the half of 100 milligrams. Okay, so now we can go ahead and solve this. Right, we can divide both sides by 100. Of course, we get 1/2 is equal to e to the 1590k. And then if you take the natural logarithm of both sides, this would be ln 1/2 is equal to 1590k. Okay, and then one more step to isolate k further. K is equal to ln 1/2 all over 1590. Okay, so now, of course, we are going to substitute this back in to the original equation that we have. So m of t is equal to 100, the original sample size, and then e to the ln 1/2 all over 1590 multiplied by t. Notice that, and this is important, e to the ln 1/2 would actually just be 1/2. Okay, so we can rewrite this equation here to be m of t is equal to 100 and then 1/2 as the base, and then t over 1590. Okay, this might be familiar from back in either pre-calculus 12 or in science 10, possibly. And now that we have this half-life formula, if you will, we can use it to find the mass after 1,000 years and find out how long it takes for the mass to be reduced to 30 milligrams. Okay, so on one side, we can simply go m 1,000 is equal to 100 times the base of 1/2, and then 1,000 over 1590. Okay, and okay, so once you do that on a calculator, you get approximate mass of 65 milligrams. Okay, and likewise, you can also be given a mass. So in this case, 30 milligrams is equal to 100 times 1/2, and then t over 1590. And once again, we can solve for t here. So we can divide both sides by 100. We get 3 over 10 on the left-hand side. We can also take the logarithm on both sides. Okay, so we'll get t over 1590 ln 1/2 on the right-hand side. And if you were to further isolate, you can get t is equal to, let's see here, 1590 times ln 3/10 all over ln 1/2. Okay, and that will give us approximately 2,762 years. Okay, so whenever you do this kind of question, it's always a good idea to think whether your answer makes sense. So 1,000 years, for example, is less than the half-life of 1,590 years. So you expect the 100 milligram sample to decay, but not quite reach the 1/2, which is 50 milligrams. So 65, in that sense, seems reasonable. Likewise, 30 milligrams is past the is past 50, so it would take longer than 1,590 years to reach that mass. And if you think about it, 100 once 100 milligram sample will reach 50 milligrams after 1,590 years, and it will reach 25 milligrams in an additional 1,590 years. So it's about 3,000 years for two half-lives to have happened. So, of course, 30 milligrams is not quite that far ahead into the future. So 2,762 years. That answer makes sense in that line of reasoning. Okay. So next one is a little bit different. The Newton's law of cooling. So it says here a bottle of soda pop at room temperature, 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda pop has cooled to 61 degrees Fahrenheit. Once again, this is a natural growth or decay question, just because cooling is also the rate of which something cools is depending on its current temperature. Okay, so it's going to be slightly different, however, this time. We will have dt is equal to k, and here t minus 44. And the reason why it's t minus 44 is because once the soda pop reaches 44 degrees Fahrenheit, and that is the refrigerator's temperature, is not going to go below that number. So there is a limit on how far it can get. Okay, so we can still apply the same logic though. So we can simply let y equals to t minus 44. So that way we can still have dy dt is equal to now ky. Okay. Now y of 0 is equal to t of 0 minus 44, because we've defined it we actually have two functions here, both in terms of time. One is temperature in terms of time, t of t, and one is simply the temperature minus 44, and we call that function y, which is also in terms of t. So if we kept going here, y of 0 is going to be equal to the initial temperature, which is 72 degrees Fahrenheit, the room temperature of the soda pop, and then minus 44 degrees, which gives us 28. Okay, so y of t is equal to 28, and then, oh, sorry, let's be a little bit clearer here. Right, so y of 0, e to the kt. We use y equals t minus 44 simply to get to this stage, so we can apply the solution of our differential equation that like we have done before. Okay, so now, of course, we know y0 is equal to 28. So we simply have 28 e to the kt. Okay. So after 30 minutes, so that's where we're going to begin here, t 30 minutes is equal to 61. That means y 30 minutes is going to be equal to 61 minus 44, which is 17. And that's the number we're going to use in our differential equation here. Sorry, our solution to the differential equation. So we will have y 30 is equal to 28 e to the k times 30. Go. So of course that means we have 17 is equal to 28 e to the 30k. And then we do the same thing as before. So ln 17 over 28 is equal to 30k. In other words, k is equal to 1 over 30 ln 17 over 28. And we can find out what that number is. It's going to be rounded. It's going to be negative 0.01663. And it makes sense that k is negative because the temperature is dropping, right? So it's lowering. All right. So now that we have the formula, we can use it to find out what the temperatures are. So in the first instance here, it says another half an hour, so that'll be 60 minutes after the fact. So y of t is equal to 28 e to the negative 0.01663 t. Now, of course, y of t is equal to t of t minus 44, so t of t, to find the temperature, is simply going to be 44 plus 28 and then e to the negative 0.01663 t. Now we can substitute in the time, which is 60 minutes in total. So T60 is equal to 44 plus 28 and then e to the 0.01663 60. And once again, we're going to use the calculator for this part. That will give us 54.3 degrees Fahrenheit. Okay, and then on the other side, how long until it cools to 50 degrees? So we can simply write 50 degrees is equal to 44 plus 28 and then e to the negative 0.01663 t. Okay, so of course you can subtract 44 from both sides. 6 is equal to 28 e to the negative 0.01663 t. And you were to go ahead and take the logarithm of both sides. So log 3 over 14 is equal to negative 0.01663 t. And then, of course, you divide both sides by the coefficient and get t by itself. T is approximately 92.6 minutes, or about an hour and 33 minutes. Okay. It's a bit long video today. We just have one more part to go through. This idea of continuously compounded interest. So let's very quickly the interest formula, right? So you have the amount is equal to the initial amount multiplied by 1 plus r, which is the interest rate per year, divided by n, the number of compounding periods per year, and then nt. Okay, once again, just go ahead A naught is the initial amount, R is the interest rate, N is the number of periods per year. Okay, so if we're looking at $1,000 being invested at for 3 years at 6%, and then if it's compounded annually, so we simply substitute in, so A naught is equal to 1,000, 1 plus 0.06 divided by, in this case, 1, because it's annual interest. And then to the third power, that will give us $1,191.02. Monthly, basically same thing. Now, of course, we're going to divide the interest rate by 12, because there are 12 months in a year. And then 3 years worth of months, of 36 months. And we'll get a slightly more interest because of the compounding. More frequent, the higher the interest, $1,196.68. In that case, daily, same thing, except for we'll be dividing by 365. All right. So this would be 3 times 365 here. The interest, the amount is still going to be greater at the end, but not by as much. So it's going to be $1,197.20. So ultimately, the question is about continuously compounded interest. It turns out, if we're looking at compound interest with that happens continuously, as a slightly different formula, it will be A of t is equal to A naught, and then e to the rt. So e is going to be our base. So this would be $1,000 e. The rate is 0.06, and then multiply by 3, and we're going to get $1,197.22. So not that much more than if it was daily, but still there is a difference. Okay. So that is it for exponential growth and decay. And it really goes to demonstrate how the number e is very useful in this kind of question. That is it for today. Thank you for listening.